Dear viewers, welcome to the UGC lecture series in biophysics. In the previous lecture, I introduced you about the Fourier methods in X-ray crystallography. This is the continuation of that lecture. It is called part 2. The starting of this presentation begins or deals with the Fourier synthesis. This is called Fourier synthesis X-ray crystallography, the famous equation which is needed to calculate electron density at every point x, y, z in the unit cell, and those points where the electron density or maxima are called the atomic sites. To calculate this electron density or Fourier synthesis, what you need is in the right hand side parameters. First is V. V is the volume of the unit cell, which can be obtained when you collect the diffraction data. The unit cell, as I have seen in the beginning of my lecture series, it is made up of 3 cell edges A, B, C, and each angle opposite to one of the cell edges, namely alpha, beta and gamma. So, total we have 6 unit cell parameters. If you know all these, volume can be calculated. Triple summation, each means for one Miller index, H, another is K, other is L, all varying from minus infinity to infinity. As I told you in the previous lecture, Miller indices are designated to define a Bragg plane. These integers can be either positive or negative, including 0. Then inside the summation we just see we have amplitude of f h k l, because we have seen that structure factor of a Bragg reflection denoting the overall contribution to diffraction by the unit cell contents is not a real quantity, it is a complex quantity. Any complex quantity will involve an amplitude like mod f h k l and also a phase like phi h k l. So, structure factor f of h k l is nothing but mod f h k l multiplied by e power I phi h k l. But in the Fourier synthesis, this is known as the Fourier coefficient, because it is a Fourier synthesis, as we have already seen, this has to be multiplied by an kernel, that is called exponent now minus 2 pi I h x plus k y plus L z. Now, what does this tell you? For every x, y, z, every point in the unit cell x, y, z, you can fix it. You vary the reciprocal lattice parameters h k l from minus infinity to infinity, for which already we have calculated intensities of reflections I h k l. After taking square root, we have this mod f h k l available with you. Only unknown in the right hand side is now phi h k l. Unless you know phi h k l, your rho of x, y, z cannot be calculated. Unless you know electron density at various points in the unit cell, we cannot determine what are those points called atomic sites which will have largest value for electron density. This equation is a Bible in electron X-ray crystallography, you should not forget anything. So, this tells you what is the bottleneck called phase problem. Then later on we will see how to overcome the phase problem. Now, we will deal with the importance of phase angles in the Fourier synthesis. As I told you, Srinivasan, the second doctoral student of Professor G. N. Ramachandran from University of Madras, in the year 1961 has carried out pioneering work on the significance of the phase synthesis and proved that the phase synthesis, by exactly feeding the phase, true phase, and by taking all amplitudes mod f h k l to be a constant value, or true phases and making all amplitude to be random values, and compared with the Fourier synthesis having exact values of phases and exact values of mod f h k l from experiment. It is a very good publication. This resembles in these 3 cases whatever I have given, no, the electron density resembles the actual Fourier synthesis remarkably well when he did the calculation on the experimental work performed on the small molecule L tyrosine hydrochloride. The heavy atom chlorine has come out in the Fourier prominently with almost the same strength as in the actual Fourier synthesis. When you say actual Fourier synthesis, I have fed in the Fourier synthesis mod f h k l coming from the actual structure and phase h k l the true phases, right. Now, when Srinivasan did it, when phases are true and if you use same amplitudes, irrespective of same amplitude for all such effect amplitudes, he got the heavy atom position at the same place where actual Fourier synthesis gave the thing. They wrote a very good paper, Ramchandran and Srinivasan, a classic paper in Nature in the year 1961, titled An Apparent Paradox in Crystal Structure Analysis, which proved the importance of phases in the Fourier synthesis. So, phase is important rather than the amplitudes by comparing two structures which are entirely different. He took two different structures. From one structure he took the phases. The structure was, let us say, B. The other structure A, he took amplitudes. By feeding the Fourier synthesis with mod Fa and phases from B, phi B, he computed and he got the structure B. It is B is the structure from where phases are taken. Therefore, from wherever you have taken the phases, that structure is reproduced, which means that and times structure factor amplitudes can be in error, does not matter. It can be same, which is actually wrong, but even if we assume amplitude to be same for all the Bragg reflection and amplitudes are random for all the Bragg reflection, as long as the phases are true, we can get back the structure. This is the importance of the phases. Results unambiguously prove that in a Fourier synthesis, the phase information is essential. It so turns out that this information is so overwhelmingly important that the approach, whatever may be the large errors in the amplitude, that can be tolerated. The Madras Crystallography group from Center of Advanced Study in Crystallography and Biophysics, headed by Professor G. N. Ramachandran, during 52 to 68 developed many types of Fourier synthesis for partially known structure. What do you mean by partially known structure? Suppose let us have a structure containing 40 atoms. Out of the 40 atoms in the molecule, suppose I know only 30 atoms, that is called partial structure. So, if you know fully all the 40 atoms, that is not full known structure. Okay. Now, when you calculate this 30 atoms out of 40 atoms, from the 30 atom positions, I can calculate one structure factor, that is known as calculated structure factor amplitude. And also from this 30 atom contribution, I can calculate a phase angle from the geometrical structure factors. So, these can be again fed into the Fourier synthesis. So, like that he has formulated different types of synthesis, all are recorded with their applications in the textbook early reference Fourier methods in crystallography by Ramchandran and Srinivasan. Now, I am going to show you a table which gives the name of the different Fourier synthesis along with the coefficients used. Again, starting is again same equation, Fourier synthesis equation, electron density at a point x, y, z equals 1 by V, volume of unit cell, triple summation over the Miller indices h, k, l, running from minus infinity to infinity, mod f h k l, which is coming from experiment, e power I phi h k l, which is not available from experiment, multiplied by exponent minus 2 pi I h x plus k y plus L z. If it is a small molecule, the direct methods proposed by the 1985 Nobel Prize winning personalities Professor Jerome Karl and Herbert Hoffman, they can provide you phase information directly from measured intensity. That is why those are called direct methods. Using that only, Fourier synthesis have been calculated. Of course, some approximations where the second stage, those can be approximated to reality. That is the case. So, like in 60s, when Ramachandran was heading, he said, why not we consider different Fourier synthesis. So, different Fourier synthesis in the sense that if you look at 5, we have used only mod f h k l as the coefficient, clear. Instead of mod f h k l, he is using so many things as the coefficient, right. That is why you are going to see the second column as coefficient. So, for example, I will explain, we will see one by one. What do you mean by alpha synthesis? Everything is Fourier synthesis only. These are proposed by Ramachandran and his colleagues. Or when you say alpha synthesis, your mod f h k l in equation 5 is replaced by mod f1 square multiplied by fp. Fp is a complex quantity structure factor, which can be written as mod fp e power I phi p. I already told you, if you know the positions of the partial structures, let us say out of 40 atoms, 30 atoms, then for 30 atom contribution to structure factor can be calculated, and that is mod fp. Then 30 atoms contribution to phases can be calculated, that is called phi p. Okay. If you use mod f1 square mod fp e power I phi p instead of mod f HKL e power I phi HKL in equation 5, that is known as alpha synthesis. Be clear. So, like that, if instead of mod f HKL e power I phi HKL, if I use mod f1 square, the second row, divided by Fp dagger. Fp dagger means complex conjugate. So, now what is a complex conjugate? Your Fp dagger will be mod Fp e power minus I phi p. So, that exponent when is taken the numerator, that becomes e power I phi p. So, that is called the second row. That can be used in the Fourier synthesis 5 before that exponent minus 2 pi I hx plus ky plus L is there. If so, that is called a beta synthesis. Then if you use mod f1 square e power I phi pi, that is called gamma synthesis. What do you mean alpha prime synthesis? Here it is mod f1 fp. The difference between alpha synthesis and alpha prime synthesis is that in alpha synthesis mod f1 square is used, in alpha prime synthesis just mod f1 is used. Okay. But fp is already mod fp e power I phi p, because now you are becoming experts in crystallography. Structure factor can be written as an amplitude times e power I phi p. What is my beta prime synthesis? Now, instead of the second row mod f1 square, remove 2, mod f1 by fp dagger. Fp dagger is what? Fp is mod fp e power I phi p, fp dagger will be mod fp e power minus I phi p. That exponent e power minus I p, when it is taken in numerator, that becomes e power I phi p. Clear. Now, gamma prime synthesis is nothing but mod f1 e power I phi p. So, if you look at the book, everything practical applications of this synthesis have been provided by Ramachandran and Raman. These syntheses have been analyzed for their peak strength and positions for non-centrosymmetric structures. Already in the beginning of the lecture, I told you what is a non-centrosymmetric structure. If it is centrosymmetric structure, for every point at xj, yj, zj, we have an atom, means at minus xj, minus yj, minus zj, same atom will be there. If you have a carbon at x1, y1, z1, then at position minus x1, minus y1, minus z1, you should have a carbon. If you have nitrogen at x5, y5, z5, at minus x5, minus y5, minus zy, you should have again nitrogen. So, this is called centrosymmetric. If not, that is known as non-centrosymmetric. Non-centrosymmetric is general case, centrosymmetric is a special case. For every atom at xj, yj, zj, fractional coordinate, you have an identical atom at minus xj, minus yj, minus zj. If this is not there, then it is called as a non-centrosymmetric. If it is there, that is called centrosymmetric. Modified Fourier synthesis was developed, and the effect of centrosymmetry was also discussed by Ramachandran and Raman in the textbook. Then the uses of weighting functions have also been studied in the case of the two syntheses, beta and gamma synthesis. For detailed survey, but is out of print, John Wiley publication, you can refer to the department, they can send you Xerox copies. It is better to go through the Wiley monograph in crystallography book titled by Fourier methods in crystallography, authored by Professor G. N. Ramachandran and R. Srinivas, if you want to know more. So, let us see what are the syntheses. I given three, this is output of a Fourier synthesis map. Okay. The central, that like your jaggery, no. So, the central electron is the contour, the central point is the atomic site, right. A phase synthesis means I am using phase true phases, amplitudes are same for all Bragg reflections. B means phase is true, amplitudes are assumed to be random. Fourier synthesis, actual Fourier synthesis, whatever you would be doing, true amplitudes and true phases. If you just see here, C is the actual case, whatever peaks I get, same things are repeated in A and B also. This shows the importance of the phases. Okay. So, whatever I have shown the graph, these are the non-centrosymmetric projections of L tyrosine hydrochloride, you can find it from the book. So, first is known as the phase synthesis, where the magnitudes of all structures are all made equal except for a decrease with sin theta lambda corresponding to a mean atom in the structure, but correct phases are used. B denotes random synthesis, the structure amplitudes are randomly permuted among themselves for each range of sin theta lambda, the correct phases are however correctly used. Third is the actual Fourier synthesis, both correct amplitudes and correct phases are used. We have to know the similarity between A, B and C. In particular, the heavy atom chlorine has come out much greater strength than the other atoms, even in the phase synthesis and random synthesis. So, this shows how important is the phase compared to the amplitude, and it also says that you can tolerate errors in amplitude, but not in phases. So, this again shows the modified beta synthesis. Already you know what is beta synthesis for the projection, AC projection of L-cysteine hydrobromide using bromine and sulfur as the known part. Then second picture is composite electron density diagram for L-arginine hydrobromide. This is known as weighted beta synthesis. Centrosymmetric AC projection of tosyl, L-prolyl, L-hydroxyproline monohydrate is given. Actual Fourier synthesis A, some function is given, alpha synthesis is given. Then AC projection of the sharpened difference Patterson of the structure tyrosine and tyrosine plus oxygen is given. The Patterson sign thesis is given. Why I am very much showing this figure is that most of the people think that Professor G. N. Ramachandran's contribution was only the triple helical structure of the collagen and Ramachandran map. Maybe some people say that 3D image reconstruction using your convolution theorem. Important contributions in X-ray crystallography in particular have been provided by Ramachandran. One is the Fourier synthesis, which we have been seeing now. Other is the anomalous scattering, which you are going to see next. Okay. So, regarding anomalous scattering, that is why I mainly focus on Ramachandran, because you must know, an Indian scientist, what are all his contributions. See, 100% mathematics. He was not at all a mathematician. He was a BSc honors physicist, then MSc by dissertation. With Sir C. Raman, he did work on some other things. He changed completely because his father was a mathematician, and before joining BSc honors, he was advised by his father that Ramachandran, you already know the BSc Max syllabus, join your BSc honors physics. So, that was his highly capable person. No? Unfortunately, he was not recognized towards his end. That is fine. So, this shows anomalous difference Patterson map calculated with maximum data set, maximized data base. I will see you, we will be clear more about this diagram, figures, maps in the next lecture series. 3 maps you are just showing. Just remember, one is known as anomalous difference Patterson map, your B is known as dispersive difference Patterson map, and we have the generally calculated position matter map. If you look at the comparisons, in the right hand side bottom of the figure, we have strong peaks, right. If you look at figure C, that is the exact peak which have been reproduced in figure B and figure A also, about which you will see later when you talk about anomalous scattering. So, these are the references whatever we have been dealing in Fourier synthesis. Ramachandran and Srinivasan textbook by Valley, then Patterson's paper, 2 papers are there. Then about the squaring method, David Sayer has given, he is also an important theoretician. Then synthesis, various synthesis, Ramachandran and Srinivasan publications are there. Ramachandran and Srinivasan, Nature publications are given the references. Then refinement of the theory and a general comparison of synthesis, again Srinivasan given a review, and if you want more you can do the website also. So, I have to thank you. So, if you want to recollect whatever we have seen here, this mainly focuses on Professor G. N. Ramachandran's contribution to new types of Fourier synthesis, and also Ramachandran and Srinivasan's work proving that phases have to be exactly known, amplitudes you can tolerate errors and so on. So, importance of phases in getting out the structure has been elegantly given. They have actually not only given the theory, but also experimental smaller structures they consider, and they have given the proof also for their theory. You are seeing 3 maps on the screen. The map C denotes the ion site positions. Okay. Like a contours. Now, what do you mean? For someone will know what do you mean by contour. Contour is a tracing of all points having the same values, that is known as a contour. Because those days no computer 3D imaging the people cannot view. So, that in order to have a better viewing, when they keep sheets one by one of this electron density, they used to draw contours. Then from upper, suppose you put 30 layers with a gap in between, from top they view the maps by having a light at the bottom. So, that is why they are putting contour. Nowadays machine takes care of everything, is completely automation, these are not needed. So, if you want to appreciate the contribution from those and want to learn the subject, you have to go into these maps. So, if you look at the map C, that is the final one. So, it is a D-sulfuridoxine protein. You have the ions given as 5 ion side positions we have shown here, the darkest one. Now, same position obtained in figure A and B, sorry, map A and B. What is map A? What is map B? What is A means? A is known as anomalous difference Patterson map. What is a Patterson? Patterson map is nothing but square it. A Fourier contains coefficient as mod FH. If you use mod FH square as a coefficient or intensities of HKL as coefficient, that is known as the Patterson. Okay. Square of the amplitude is known as a Patterson. Suppose we use square of a quantity equivalent to difference between two Satcher factors, that is known as difference Patterson. So, it is not just the amplitude mod FO minus mod FC. Okay, let us see, observed Satcher factor minus calculated Satcher factor. If you square it, that is known as a difference Patterson. Okay. Now, anomalous difference pattern. What is anomalous difference Patterson? This is what we are going to see in detail in the next lecture series. Whenever the incident frequency of the X-ray radiation is equal to the natural vibrating frequency of an atom in the molecule, then the atomic scattering factor becomes a complex quantity. The consequence of this complex nature of atomic scattering factor is to violate a well known law in X-ray diffraction known as Friedel's law. Friedel's law states that intensity of HKL reflection is always equal to intensity of minus H minus K minus L or intensity of H bar K bar L bar reflection. But this is not true. As long as the incident wavelength is far removed from the absorption edge, that is true. But if the incident wavelength of frequency is nearing to the absorption frequency of a heavy atom, then we have the complex nature of atomic scattering factor in the heavy atom. The consequence is violation of Friedel's law. We talk about intensity of HKL not equal to intensity of H bar, K bar, L bar. So, this difference in the intensity between HKL and H bar, K bar, L bar was made use of in calculating the position of the heavy atom, which contributes to this. And this work was done in the year 1956 again by Ramachandran Raman in Chennai. Same year, same work was done by Professor Peterman and Byford in the University of Amsterdam, the Netherlands. So, that is again unfortunate thing happened in GNR's discovery. They have published the results, GNR's group, in Currents in 1956. So, here we talk about, since I of H is not equal to I of H bar in anomalous scattering, mod FH will not be equal to mod FH bar in anomalous scattering. Therefore, mod FH minus mod FH bar will have a value. If that is squared, that is known as the first map A, anomalous difference Patterson map. That is one thing. So, like that, if you tune the wavelength, the incident wavelength is coming next to the absorption frequency and also far away, the Satcher factor changes will be enormous. Now, between the two wavelengths, you can use that Satcher factor, unequal Satcher factor differences can be squared, that is known as dispersive difference Patterson. All these things we will deal later in our next lecture series. Thank you.